All right, well, I guess we're about ready to pick up on part 2 here. We last left off with my Ford Torino moving a little bit further down the road. So we're going to take acceleration a little bit further this time and take our definition of acceleration, our symbolic representation of acceleration, and we are going to juggle it around a little bit. Any one of these equations could be juggled around to present it numerous different ways. The way that they represented on the formula sheet for you is the one that you see in red at the bottom of the screen. So it's a good one to get used to, and it's really the first kinematic equation that will be given to you on formula sheets for my tests and quizzes and also for the AP exam, and it'll be in a format that looks almost exactly like that. Okay, so here is another problem that you could try here, so please pause and give it a try. And you're back, and the answer was 45 meters per second. How did you do? If you had troubles getting that, give it another try, or we'll go over it in class. Time to hit the pause button again, though, and give this one a try. And we're back, where the answer should be 14.6 seconds. How did you do? How did I do? Well, time will tell. Okay, so let's see what else we got going on here. Acceleration and distance can be put together in one equation. Now, here's a challenge for you. Can you take what I've shown you so far and make the connections to see where this would be the next equation? Give it a try. This is what you're going to come up with, and it's a pretty strong skill if you can do that. And we'll do it in class, but give it a try. That's a good one to challenge yourself early on. Okay, so here's one that uses the new equation. Set it up with the variables, show your work, hit pause, and when you come back, like now, the answer would be 80 meters. How did you do? Okay. So here's another one that uses that new form of the equation. Down the road, the skill will be to pick which equation you need to use, but here it's the new equation. So let's see what you got going on for this one. Pause, and the answer should be 200 meters per second squared, which brings up the question, what kind of object could accelerate at 200 meters per second squared every second, almost 400 miles per hour faster than the second before? What kind of object? If you said spaceship, you're off to a good start. Woo! That's pretty good. Okay, let's see. Another equation, and again, I challenge you to try to derive this equation yourself. Try to take what you've already learned and put it into this form. But at any rate, that's a form very similar to the third kinematic equation that will be given to you on formula sheets. Not quite yet, though, so here's an explanation. D can be distance, and it's a very useful equation to think of D as distance. It's also convenient to use D as displacement. And if you remember, a displacement is a change in position. And since a change is the final value minus the beginning value, displacement would be a change in position. Here, we're representing position in x. Maybe picture it on a graph or a number line. X final minus X initial. And the reason I'm doing that is because that's the way they present it on the formula sheets, and that's what you'll be seeing on all of our tests and quizzes this year, and on the AP exam if you choose to take it. It's convenient in most cases to just think of it as D, but that's the explanation for what you'll see on the formula sheets, and I want you to be prepared for that as well. Okay, one-dimensional motion is motion in a straight line. So here's a couple cars going down the road in a semi-straight line anyway, but just to illustrate the idea of straight line motion. Now, there are different ways you can represent this, but if you're talking about one-dimensional motion, you only got two directions. You can go straight up or straight down. You can go to the left or the right. That's about it. Backwards and forwards. Only two directions you can go if you're limiting yourself to one dimension. So pluses and minuses, just like that number line or the graphing that we're used to, are used to set this up. Now, it's arbitrary which is positive and which is negative. Very useful to talk about it mathematically in those terms, but definitely arbitrary to talk about those directions. And I'll mention more of that in a little while too. So this is why the v is used for speed, and you probably already knew that, because velocity is another word for speed that we use interchangeably. In real life, or in the real world, let's say, in physics there is a distinction, and velocity is going to be a speed with direction. So we could certainly talk about velocity in the negative direction, or velocity in the positive direction, to distinguish between the directions we're headed in. Okay, acceleration is also going to have a positive and a negative. Now this gets a little bit dicey and maybe confusing at first, but we can all work it out together and we'll make some sense out of this. Now, intuitively for me, negative acceleration would mean slowing down, but that's not always the case. If you have a negative acceleration and you're moving in a negative direction, it means you're picking up speed. So if the velocity and the accelerations are in the same direction, then you are picking up speed. If the signs are opposite each other, then you are slowing down. So that's the deal there. And again, we're going to work that out over many examples, including the one you're about to see. Here's an interesting case of one-dimensional motion, and that's stuff that moves in a straight line through the air. So we call those free-falling objects. So an object that is falling straight down, or an object that is thrown straight up in the air, or an object that isn't so freely falling because it's thrown down and then it free falls. But an object falling through the air is a good example of one-dimensional motion if it's in a straight line. And there is something interesting going on with that because objects that are falling through the air are subject to gravity. And it used to be a debate on whether objects pick up speed as they fall or whether they fall at a steady rate. And we've come up with the idea now that objects accelerate as they go to the ground. They pick up speed as they're falling toward the ground. Now, the acceleration due to gravity on sea level is about 9.8 meters per second squared, and most of our planet is subject to that 9.8 meters per second squared. Even high up in mountains, you have to get it pretty high before the number changes slightly. So we'll use 9.8 meters per second squared to talk about things on Earth and the way they accelerate. Okay, so special is this number that it's given a special letter, g, the small letter g, to indicate the local acceleration due to gravity here on Earth. And that's going to be different on different planets, but here for Earth it holds up pretty good, so it gets a special letter. In the equations, you'll plug it in place of a. So that's going to get a little bit tricky on this example that I'm about to give you. Let's see how you did. In this example, I'm throwing a ball up in the air. A person is throwing a ball up in the air. And I want to know how long it's going to take to get to its high point. Mathematically, it's not too hard to solve. But how about putting together all the variables? Why don't you pause and give it a try? And if it worked out, you would have come up with what I did, 2.04 meters per second. Oh, I'm sorry, 2.04 seconds, right, would have been the time. That's a little tricky, so if you had trouble with that one or any of these problems, we can certainly go over them in class. Okay, well I have one parting question for you, and first of all I'll show you somebody that has had a big deal to do with physics, and that's Galileo. I'm a big Galileo fan myself. He changed the world a whole bunch, that's for sure, and right around the 1600s he developed all these things that we're talking about right now. So this is old news, but not as old as people. People were around a lot more time before Galileo was around. So why? Why did it take so long for kinematics to get developed? Why didn't it happen earlier? So there's something for you to think about. One other thing that I want to mention about the formula sheets. I've now explained the x and the x minus naught on the formula sheet, and where you'll see that in place of d. Another thing that you'll see is a little subscript for an x. And that subscript x is talking about the idea that all of these equations really only work in one dimension at a time. And there they're picking the x direction. It could just as easily be the y, or the z for that matter, or any other letter that you might want to arbitrarily come up with to represent the idea that it's going in one direction. But I do want to explain that little subscript x on the formula sheets. Well, thanks for listening. That'll do it for now. We'll see how it all plays out in class. Look forward to seeing you there.